Welcome to the 1999 Game Developers Conference. This meeting was held in beautiful San Jose, California from March 15th through the 19th, 1999. This is recording number 113. Don't starve that CPU. Making the best of memory bandwidth.
And start to get started once I pick up the rest of the microphone. If you have your proceedings, which I guess woe unto you if you're going to carry the phone book around for 3 days, but if you have them, all these foils, except for the few I've added, are in there, and I think it's around page 670 or something. There's also a 20-page paper that goes along with this that I think starts on page 639. If I were you, I'd read the foils and get back to the paper if necessary. The paper is basically the foils with grammar that the Microsoft Word processor likes stuck in between them. So you'll probably get more out of the foils than the paper. I always do. I hope everyone coming in has one of these evaluation forms. Please fill them out. Tell us if you like us, you hate us, you liked what you saw, you liked it, what you didn't see, you wanted to see other things, how we did, etc. I eventually get these after much prodding and pushing and pulling. So any comments you do write down here. As we say when we play test Age of Kings all the time, don't be positive and don't be negative, be constructive. So if it's positive or negative feedback, always say what that means, just don't say it sucks. Tell me why it sucks. That is significantly better feedback. Okay, we'll go ahead and get started this morning. One of the interesting things about giving a talk at GDC, is this loud enough? Can people in the back hear me over the... Okay, great. One of the interesting things about giving a talk is that when you send a talk in, you usually do it about 5 minutes before midnight on the day the deadline's due. And then when you finally get it back and they say, hey, you're going to do a talk, you think, oh, that's terrific, that's great, I'm going to get out there, I'm going to do all this awesome stuff, and then you're struck with the terrible realization, what did I sign up for? So there are some things we talk about in the abstract in the actual proceedings book. And so I went around and I talked to all the wonderful guys that I work with. And you too could be one of those guys because we are hiring. And basically decided that probably the best thing that would help people coming to this session because of our experience going to GDC was talking about our experiences in trying to optimize memory bandwidth, trying to get stuff into the processor or stuff to the video card in a lot of ways because, of course, we're working on a new 3D engine. I am a 3D programmer, optimizer, plug-in writer, jack of many trades, and ensemble. And we're working on a new 3D engine to go beyond our current 2D engines, which we have shipped with Age of Empires, and we're working on Age of Kings, which will ship this fall, which is probably the question I'm asked most during this conference. So we're hoping to ship that and slip everybody's schedule by 6 months. So what we'll be talking about is that in our 3D engine, we of course process a number of vertices, we have all these transforms and such. So I'll be presenting some of the data and analysis that we did in order to try and optimize our geometry pipeline. For the second half, I'll be talking about some of the things that we did to try and analyze, for example, how best we could do procedural textures. Because we wanted to update things on the card, and we said, can we do things like, for example, Blit? And that's the data I'll talk about today. And we found out that, well, not really, because it's really going to be not good on some cards. If you have any questions at any time, please feel free to raise your hand. If I'm not clear on something, if I've misspoken something, you're unclear on a concept, please raise your hand and ask. I may not get your question as soon as your hand pops up, but as soon as I flush my queue, I will call on you, because I can see it at the back of the room and I'm not blinded by the lights. So the first thing we'll talk about is we'll briefly talk about the front side bus and basically the memory to the CPU interface. We'll just cover some basics. Should be pretty basic to people in here. Some people go, oh, that's old hat to me. May not be old hat to other people in here, so just bear with us for those few slides. We'll get right through them. Then we'll talk about the data structures that we went through, different data structures that we looked at based on what we implemented and as well as what we've seen other people implement in various 3D engines. Previously, I worked at Intel for a while and went around to various game companies and looked at different people's interesting implementations of things. And so I've grabbed a few of those data structures and put them in, and we did some tests on those. Then I'll talk about batching processing. In other words, what are some of the benefits of doing transform lighting, clipping for one set of vertices all after the other, versus what are the benefits of doing all your transforming, all your transforming, all your lighting, all your clipping, etc. And I can comment here and there, and people are certainly free to ask questions on how it affected our engine up to a point. I can kind of talk about it, kind of not. From there, we'll flip over to the main memory to graphics card side, and then again, we'll do a brief catch-up on everybody to talk about main memory, PCI, AGP, how the whole thing fits together. I know when I've talked before on AGP that some people have had misconceptions on how things work. It's quasi-magic, and it's quasi-just bad specification. Then we'll talk about actually the performance that we've seen moving stuff between main memory, local video memory, and non-local video memory, or AGP, as Intel likes to call it. There's still some unanswered questions that this doesn't answer. There's certainly a number of things that we can't answer right now because we just haven't built the tools. Talk about collateral and bibliography. Obviously, it's in the proceedings if you have them. All the foils are in there except for the few I've added. All the foils will be on our Ensemble Studios website. We'll get you those URLs. They are in the proceeding as well, and all the source code. And I think 40 megabytes of Excel files, which I generated to make all this data. Which, for those who know me, is about an order of magnitude less than I would normally generate. Okay, so let's talk about the front side, memory to the CPU interface. This is just real brief, real high-level information. This is the typical Intel Pentium 2 architecture. All of our machines in-house are Intel Pentium or Pentium 2 type machines. We don't have any AMD stuff in-house. And that's mostly because we run 3D Studio Max, NT, etc. We don't want any surprises. So basically, these are the test platforms I use in order to generate all the data here. Intel Pentium 2 processor, 400 and 450 megahertz. Processors, Intel 440BX chipset. What that means is that's the 100 megahertz SDRAM frontside bus interface. So that's about 800 megabytes a minute, 800 megabytes a second. Boy, somebody else's CPU is probably 800 megabytes a minute getting into the CPU. And my machine had 256 megs of RAM, which is barely enough to run 3D Studio Max. Now, we talk about things like memory throughput. One of the things to note is that a cache line for the Pentium 2 series is 32 bytes per cache. And basically everything inside the Intel platform is based around optimally moving 32 bytes at a time. Whether you're an AGP card or a CPU, you're basically served the same way. So basically, if your AGP card requests a lot more than 32 bytes or a lot less than 32 bytes, it's a non-optimal implementation for those hardware people here who are thinking, is that why we can't texture out of AGP memory? So the CPU can access main memory about 800 megabytes a second, but on the other hand, the CPU can access its own onboard L2 cache in excess of 1.3 gigabytes a second. Now, it's a bit more performance, and so you see right there we're losing at least half our performance just going out to main memory to fetch something. Not only that, but it's also not only, half the performance, or just about half the performance, but we're also taking a significant hit. It's about 4 clocks to access something that's already in the L2 cache, but it's something like 39 clocks or a little bit more to access something that's out in main memory. So you're paying a 10x performance hit right there. One of the interesting things to note is that the original Celerons, before they came out with the Celeron A, didn't have cache, but neither do supercomputers. Unfortunately, supercomputers have, or fortunately, supercomputers have performance, and the Celerons may or may not, depending on your application. The big thing there is, however, is that supercomputers actually have main memory bandwidth. And that's certainly one of the things that I wish people like Intel would get to in the future, is that, screw this whole thing with cache and everything that we try and do to make cache so much better. Just give us this huge, awesome pipe to main memory and be done with it. That would be the best thing they can do to simplify all of our lives. Now, the interesting thing that usually comes up is that, what can I do about the L1 cache, which is only about, 16K data, 16K code. Not much, really. It is so small and turned over so frequently that really the processor needs to deal with that itself. With the L2 cache, at least, there are some things you can do in your code. Yes?
I was going to let you finish your cue. I'm back to the main memory access speed versus the L2 cache access speed, and the 4 clocks, 39 clocks question. So are you saying it takes 39 clocks to get it going, and then it'll crank at 800? Or are you saying that for that 32 bytes, I'm doing 800 megabytes a second, but then I got to pay another 39 clocks for the next?
You've got to pay 39 clocks for every cache access, for every cache line access outside of the cache. So that's a significant.
So it's not really-
Oh, I'm sorry. Let me repeat the question. The question was, is at 39 clocks a start off? So I pay 39 clocks the first time I access a cache line, and every subsequent cache line I don't pay the penalty for, or do I pay 39 clocks per cache line out of main memory, or a 32-byte cache line? And the answer is that you pay the 39 clocks for every 32-byte cache line coming out of main memory.
So I can't really get 800 megabytes of memory, 800 megabytes out of memory in 1 second. It's just that for tiny pieces of time.
The question is can I really hit 800 megabytes a second? In peak performance, not sustained, peak performance you can hit 800 megabytes a second. Just as out of the cache, peak performance, you can hit in excess of 1.3 gigabytes a second. Of course, then we run Windows, and that disturbs our cache consistency. Talking about the L2 cache, like I said, there's certain things you can do in your code in order to make the cache consistency better, pull things in before you need them. And that's really what you need to do is amortize, make sure the data's in the cache before you actually access it, and then you pay that penalty then. Pay the penalty before you actually need the data. There are certain things in the these streaming SIMD extensions, or whatever Intel's calling them this week, that actually do cache warming for you. But I didn't talk about those for a couple of reasons. First of all, they've just been under NDA until, I guess, the last small period of time. The second thing is that it would be an entire hour or multi-hour unto itself, because the issue is that it can make some situations better, but it's kind of like juggling with a couple of sabers. You know, you can do it, you're going to look real cool for a while, but you're probably going to, run it through yourself at some point. So it's a very dangerous thing to use if you're not totally cognizant of what you are doing. Some of the other interesting things, just to finish this up, memory types, some people may not know these, is that on the Pentium 2s, everything is controlled by these memory type range registers. Most memory is what's called write back. That means it's using the cache to read and write, using this MESI modified exclusive shared and valid, and I'll give you some references to go to actually look up more on this. There are some things which are uncacheable, which means that it always goes out to the bus and you always take a major performance hit. The interesting thing that people should remember out of this, besides write back, is WC or USWC, uncacheable speculative write combining memory. And this is how the frame buffer of your video card should be mapped. I don't know if people have been around long enough that they remember when the original P Pros came out, and there was this little utility that would basically speed up your video card. What that did is it ran and changed the MTRRs so that the memory type for your frame buffer was changed to write combining instead of write back. So that gave you a significant speed up in write access. There's also write through and write protect. You really don't run into those anymore, but like I said, I'll give you a reference that you can actually get more of this information. Okay, so we all now know everything we need to know about main memory, or most things. So let's talk about the actual data structures we took a look at. We know that getting data from main memory is slow, and using data from the cache is for best performance. So what I did was I specifically took code out of our engine, and we basically do a 4x3 matrix transform. Usually we only have about 200 to 400 vertices in a particular model before we move on to the next model in our 3D engine. Unfortunately, using 200, 300, 400 vertices was not enough in order to get actual reproducible statistics under Windows 98 on a Pentium 2. So I had to bump that up in order of magnitude to 2,000 vertices. Everything is still the same, but all the data looks consistent now. So basically what I did is I selected 5 different vertex representations and said, well, okay, what are the data structures I've seen? What are the data structures that is possible to implement? And what is the performance of those data structures as we run them through the transform loop? So using vtune 3.x's pause and resume API, a little documented thing I wouldn't have known about otherwise, unless I knew somebody, I took the data for data memory references. So this is the actual number of cache lines that it goes out to main memory to get. L2 cache request misses, which are highly correlated. This is not a statistic you can directly get, but vtune will do some magic and get it for you. And L2 cache requests. So what this will tell me is this will tell me how many times I went out to get something, how many times it was in the L2 cache, and how many times I missed the L2 cache. And then I also used the, so that was one experiment. The other experiment was to run the same code, but instead of doing the CPU counters, I used the timestamp counter to actually time the execution of the loop as well. Make sense? Okay. These are the data structures that I used. I creatively called them the structures S1, S2, S3, and S4, and I called the class C1. I thought afterwards, actually after all this stuff had been shipped off, that I should have added a C2. One thing people may notice about this class is this is a very simple class. It does not have a virtual function in it, and it does not derive from a base class, which is a virtual function. For those who know the ins and outs of of what your C code gets translated into, if you have virtual functions, you'd have to add an extra D word to the overhead of this class because there would be a vtable pointer. But we can discuss that more later. Anyway, so this is what the data was taken on. Basically, as we can see here, structure S1 is just the X, Y, and Z. That's all I need for a transform. I don't need the lighting coordinates, I don't need the normals, I don't need anything else. Structure S2, this is what I've seen in a lot of people's apps, and when I first came on board at Ensemble, this was basically the structure that was in place in our engine before I started destroying it. X, Y, Z, the normals, texture coordinates, color values, specular values. S3 is a little more bigger form of that with the actual viewport divided coordinates in it. And then struct S4 is an array of pools. Pools of X values, Y values, Z values, and then transform values. Make sense? Okay. Basically, I ran each of these tests 10 times. So basically, on the left is kind of like pseudocode, on the right is pseudocode. So I ran 10 times. I made sure invalidating the cache in this case. Ultimately turned out that was exiting the program because I ended up using vTune's pause and resume APIs, or resume and pause. You can start vTune out of pause, so it won't do anything until you actually get there and say resume. It'll start doing the counters, and then when you say pause, it'll stop doing the counters. And then we ran this test 10 times. And in the middle, this is where we actually did our Vertex transform. And this test was repeated for each of the 5 Vertex sets. So let me get my head out of the way so I don't blind myself. Okay, this is the data that we ended up with. So this is for 2,000 vertices. Structure S1, this was just X, Y, and Z. Basically, there was 4 cache misses, 7,500 cache requests out of 19,000 main memory references. So what this tells me is that's pretty good. S1A is interesting. It's a little bit better, kind of, in some ways. I'll talk about what that was in a minute. That wasn't a change to the data structure. That was just a change to the actual code itself, to the implementation. The structure was good. I mean, all it had was, it was a basic class. I'm sorry, C1, basic class, X, Y, and Z, no virtual functions, not derived from a base class. Not as bad as some might think. Some people think that C++ is utterly evil for whatever overhead that it gives you. It proves in at least this case that it's not that bad from just using a struct itself. Although we preferred the struct, we ended up preferring the struct implementation for various other engine reasons. S2, we'll move these up a little bit. S2 is the structure, like I said, we were originally using in our engine. The X, Y, and Z, normals, and everything else. So you can see that structure alone, we had 21 cache misses, 12,000 memory requests, because of course these structures are much larger, and 20,000 data references to main memory total, as opposed to just our 19,000 for the original structure. All the way up to S3. S3 was the mega structure, as I call it, that basically contained everything but the kitchen sink. I've seen people stick even more into their Vertex formats. And that one took 452 cache misses. So it was 452 times that you had to pay the penalty of 39 clocks versus S1, where you only paid the penalty 4 times. Now, some of the characteristics of this is that the total number of data memory references is approximately the same between the best and worst cases. But the best case has less than 1% of the cache misses as the worst case. Now, one of the interesting things we need to factor in is that we need to look at timing performance and other factors. For example, this was just looking at memory references and cache misses. There's certainly more statistics I could have done beyond this. This is why I normally end up with hundreds of megabytes of data when I do these things. It's also that in this case, this is totally optimal performance. One of the things you may have noticed in the code is that we elevate ourselves to high thread priority, high and real-time critical, before we go in and we sample our data. And then once we're done sampling our data, we exit back out to normal priority or resume whatever the priority was before we went into this loop. So this is the absolute best case. This doesn't mean when I actually have it in my application, I'm transforming, I'm lighting, I'm doing sound, I'm doing input, I'm doing network calls, Windows is running, and Windows has a while one loop that just invalidates the cache, that I'm going to get the same kind of performance. But at least I know where to start with. Now, one of the interesting things is that the difference between S1 and S1A, which was still using just the XYZ vertex format and nothing else, the only real difference there is that we just got rid of one of the variables. Instead of using a separate count variable and counting up to n vertices, we just use a pointer and we happen to count backwards. You could have counted forwards. Some people think that counting backwards is better. It may be, it is in some cases. In this case, I don't think it would have mattered much. But basically what happened was we reduced the number of references just by getting rid of that extra variable, that extra D word. So what this means is we had to take our original data, which was, like I said, very similar to this struct S3, XYZ's viewport, I forgot W in there. Obviously, I can't compile the power. Actually, I could compile PowerPoint. You know, VC6, you know, you can just run PowerPoint in your IDE, and it just really lags. Normals, TU, TV, coordinates, RGB, and specular. So what this meant is that we said, hey, wow, if we only keep the homogeneous data together rather than one big heterogeneous structure, we can get higher performance. So what we did is we actually restructured our data and we need the vertex, we need that for things like transform, we need the color for things like lighting, as well as the specular. We may need the normal there, but we certainly don't need the normal for transform. We don't need the normal for, we need the normal for backface culling, as well as probably a vertex, but we certainly don't need the colors. We don't need the texture coordinates probably until clipping, or if it's unclipped, we can just pass them right down to the hardware. So we basically ended up with a structure, which I just creatively called object, just to confuse everyone, that basically had pointers to homogeneous data pools of vertices, transform vertices, normals, texture coordinates, color, and specular. One thing to note here is this is the way we did break up our data in the middle. This is not how we ended up with the actual implemented data structure. I will make that note. We have what I would call a, for those familiar with OpenGL, kind of an ICD, our own ICD rendering layer, so that we can try and reduce the number of copies within our engine. So the data wasn't exactly structured like this, but as far as we're concerned, it may as well have been. Okay. So in terms of what data we need, when we backface call, we need the normal to the face. We may need a vertex, depending on how we're doing our culling. When we transform the vertices, we need the vertex itself, and we need somewhere to stick the transform vertex. When we light, we need the color, we need the specular. We may need the normal, depending on what type of lighting we're doing. When we project, well, we only need a transform vertex, and then we also need some place to stick a projected vertex. I didn't go into projected vertices because that would just complicate things, and everything just, it doesn't add anything to the data we've already done. Just take everything we've done so far and apply it to projected vertices and everything else on down the pipeline. Clipping, we do need everything if it's clipped, but if it's not clipped, we only really need the projected vertex and the other data, TU, TV, color, specular, etc. So basically that describes how we looked at optimizing our data structures. Now that was data structures. Now the next thing I'd like to talk about is now that we have our data structures optimal, what do we do with basically data flow, or how did we restructure our processing in order to get optimal performance? Okay. So here we basically have a couple of cache lines. Our X, Y, and Z data, so here we see 1, 2, and then the third vertex straddles C1, C2, 4, 5, and then we have another part of the sixth vertex that would straddle the next two cache lines. So like data is already processed together. If we only process one vertex, let's say if we took the first vertex and we did the transform, and then we did the project, we did all the steps at once, well, we'd probably destroy our cache consistency, because by the time we got back to do vertex 2 would already be flushed out to main memory. Somebody else would have already opened up pages that were brought in. So processing only a single piece of data at a time certainly wastes the cache improvement we've made. And by performing all the single tasks on all of the homogeneous data we have, such as the vertex, before moving on, we can keep this cache consistency that we've established. So here is the actual, for example, this is the old way that we did it. We did our transforms, so we had a cache miss when we loaded the first vertex in, and then we had a cache miss when we wrote the vertex out transformed. Then we projected. So the vertex we transformed was already in memory, but the projected space we were writing it to was a cache miss because we needed to write it back out somewhere. Well, then we go to light, but we didn't have the normal in memory, I mean in the cache, so we had a cache miss there. Well, then we needed somewhere to write the color to. We had a cache miss again. And then we finally did the clipping, and this is in the not clipped case, or the, in order to clip it, we had to read the projected data back in, which we'd used up in the project phase, and this would be doing projection space clipping. Obviously, if you were doing transform space clipping, this would be up higher, so you may save a cache miss, maybe. But anyway, but the intent here is that basically we had a lot of cache misses, and we just totally destroyed the cache consistency that we had otherwise established. So basically, we did a lot of restructuring, and we halved, or actually, again, this is the basic stuff. Can't talk about how far we ended up optimizing the engine at this point. I mean, we're still very early in the development process, but we run real fast. So we transform a vertex, we transform all the vertices with this cache consistency. That would basically be doing like the transform loop that you saw earlier. And then we do the projections, then we do the lighting, then we do the clipping. Actually, we've switched to doing clipping in transform space rather than projection space, and so on. But basically, we have this cache consistency. We're making sure we're bringing things into cache, and that we were trying to be very nice to keep things moving to the CPU, because the main memory is the big bottleneck, and it's going to continue to be the big bottleneck for the foreseeable future. It's the bottleneck getting things from main memory to the CPU, and it's the bottleneck getting things from AGP and main memory to the AGP graphics card. So in summary, for the first half of the talk, analyze your data usage, layout, and data flow. Keep data that's needed at the same time together in memory. This can complicate your data structures, but it can also significantly improve performance. Again, we decided to pay the penalty up front and restructure now rather than wait until some point in the future when we actually got close to shipping an app and then pay the price. Process data in batches. Don't destroy this cache consistency you've established. Watch out for cache alignment and data layout issues. That's also something I did not go into. That itself would be a multi-hour topic. Use sampling and, in my case, and instrumenting profilers. This data was taken with vTune. And I think the question, well, what do we use for performance? First level, we run something like TrueTime, which is an instrumenting profiler. And that basically tells us what is happening in our program at a high level, function by function. And then when we drill down, we use the pause resume API of vTune to actually drill down into a specific function. We found that because of the number of things that get loaded in with a modern 3D engine, if you ever just run a vTune display, if you're an NT, go in and look at the number of tasks that are loaded between DLLs, executables, and whatever, the vTune results can be interesting at best. Some would say spurious, I would say interesting. And use CPU performance counters. I think the more that we can drive not only the CPU manufacturers, but the video card manufacturers to give us performance counters up and down the pipeline, the better data and the better informed decisions we can make. So are there any questions before I go on to the next part? Yes?
Take it from one of your diagrams that the Pentium cache doesn't do any kind of write buffering?
The question is, does the Pentium 2 cache do any kind of write buffering? Yes, there is write back memory type. mention, I don't know if you were here for that part, that I will give some references so that people can read up more. Usually what happens is when I lay out my slides, I end up with like 6 hours of data to compress into an hour, and already I'm running at like 1 slide a minute to try and get everything down, because I certainly think it's more interesting than me sitting here and talking about one slide that you can't read for 5 minutes. But we can certainly discuss some of the ins and outs of that as soon as we're done. Yes?
Any rough numbers on frame rate increase or something that you saw by restructuring the way you did?
Were there any rough numbers that I can discuss on frame rate increase? I can't specifically speak to that, but let's say, oh, we rock.
Can you give us a ratio? Because the only ratio we've seen so far...
Multiple hundreds of percent.
Okay.
Multiple hundreds of percent. It's hard to separate out some of this in our initial process phase, and I can talk about that for a couple minutes, because I'm running a little bit ahead, because I don't want to bore people with data that they may already know. So that's why it's good to ask questions. Is that in the initial optimization phase, not only do we use TrueTime and VTune, but we also have our own in-house profiling stuff, which basically we can mark large sections of code. And that was the original stuff I wrote before I found out about TrueTime, and then Newbeg has been very good about fixing issues that we had with it. So I would highly recommend it and highly recommend their support people. I must give them a kudo. What happened is that not only did we find that we were spending a lot of time destroying our cache consistency through having heterogeneous data all stored together, we were also destroying our cache consistency and destroying performance through basically redundant initializers in class constructors. And that's something VTune will certainly not show you. So we spent a lot of time there. We also spent, or I also spent some amount of time doing recoding and assembly. Float to long conversion is definitely a killer. We took all those out. And then doing color conversions, I hand coded all that in assembly. So that's basically everything that was done at once. And I can qualify this as being multiple 100% of increase in performance. Yes?
Would the alignment boundary make a difference for those structures?
The question is would the alignment boundary make a difference with those structures? These structures are small enough that alignment is generally not an issue per se. If you had a larger structure and certain data requirements, these are also D-word aligned. I mean, if we're using IEEE, single precision floating point, they're all D-words. If you had data which was interesting, let's say cares, unsigned shorts, all kinds of other stuff, then I would be more worried about cache line alignment. Certainly one thing you can do in order to fix problems like that is to write your own memory manager. And it is certainly something that we have addressed and worried about in various parts of our engine. Okay, well let me go on to the second part then. From the CPU to main memory and back, and what the performance characteristics were there, and how we could actually change your application. There are certain things, basically, when we were dealing with the CPU, of course you can program it. Some people's video cards you can program, and the way they release driver updates, you can think you can program it on a weekly basis, but basically what it means is that you can take a proactive stance on the CPU side, because you can actively change your code and say, hey, I can make my code better. On the video card side, you basically have to take a reactive stance. X sucks, I need to do something else. And I know we've all encountered that. I mean, as long as 2D video cards have been around and supported an allegedly complete and specific set of features, there still continue to be certain bugs. And certainly when we shipped Age of Empires last year, one of our guys, Matt Pritchard, certainly spent a lot of time having to specially code to say if it's video card X, well, we can't do this. With video card Y, we can't do this. And so we're still in the same position. So what I'd like to talk about is, again, briefly go over PCI and AGP, give basically the same kind of high-level overview. Again, maybe redundant for some, but I'd like to get us all on the same page. And then talk about performance characteristics we found when blitting between different types of memory services. So first of all, what's PCI, the Peripheral Component Interface? And I'll give you some, again, some references that you can go to get more data on this. Well, there's a couple things you can do here. There's memory mapped I/O, and that's the ability for you can already read and write to main memory. You can also map memory on the card and make it look like main memory for all intent and purposes and read and write to that. That's how most people do these control registers, 2D registers, 3D registers, basically. And basically, the CPU has to push data to the card or pull data back out. There's also direct memory access, and basically that takes the onus off of the CPU in terms of moving data. And the graphics card, could be a NIC, could be anything out there on the PCI bus or an AGP, then has the need to actually pull the data out of main memory. And it takes the load off the CPU. That's very good. The more load you can take off the CPU, the better. It runs at 33 megahertz or 66 megahertz for workstations, which is known as fast PCI, or AGP frame, and we'll get to that in a second. And the bandwidth at 33 megahertz is, most people don't realize that you're only transferring a D word per clock. Wow, you got this huge fast computer, I'm only transferring a D word? That's not sexy, but it is 132 megabytes a second. So what's AGP? Step one, copy the fast PCI spec. We wouldn't want to reference it. For those in the hardware industry, they know exactly what I'm talking about. Fast PCI, 66 megahertz PCI, is known as frame-based AGP. Basically, one D word is transferred per clock, and so that's 264 megabytes a second bandwidth. These are all peak numbers, by the way. Your mileage may vary, and probably will. This is also known as AGP 1X mode, but I will get into the modes. I'll show you this whole daunting chart and tell you why we're all so screwed when we try and buy video cards. Step two is transfer 2 D words per clock. So basically, the way that the original spec works is on the rising edge of the clock, you transfer 1 D word down the bus. The way that AGP 2X mode is that you transfer a D word on the rising edge of the clock, and you transfer a D word on the falling edge of the clock as well. So now that gives us 528 megabytes a second. And we could keep sampling that down to finer and finer intervals, just as long as we could keep basically the latency or the skew in the hardware under control. Now, one of the other interesting things that this gives us is this gives us access to non-local video memory. And what this means is that main memory can be reserved by AGP for things like commands, data, textures. Technically, you could put something in the AGP port that was not a video card, NIC card, sound card, what have you. Because all it is just one big memory pool. Now, AGP can request all physical memory up to the minimum of either physical memory minus 12 megabytes, so if you have a 24 meg machine, that's going to take half of it, or whatever the AGP aperture is. So let's say you have a 128 meg machine, your AGP aperture, which is settable in the BIOS in most machines, most notably not Gateway, is, like, say, 64 megabytes. If you have a 128 meg machine, it can take down to 64 megs. Or if you have let's say, a 48 meg machine and it's set to 32 megs, you can only take 32 megs of that. So that's the way it basically works. Most everybody only will work with 64 megabyte or higher aperture. Non-local video mem, AGP, same thing. Basically, there's something that you should know about called the graphics address relocation table, which is located in the memory controller. So that AGP memory, just like when you request memory, if I do a new and then I do another new, or I do a malloc and another malloc, those pieces of memory probably won't be contiguous. And the same thing is true of AGP. So there's this thing called the GART, which acts as a scatter-gather mechanism. In other words, it takes random pieces of memory that have been allocated that are non-contiguous and makes it look to AGP as if there is one contiguous logical space of physical memory. This cannot be paged to disk, and this is one reason that if you are running in a low memory configuration, or let's say you are running so that your AGP aperture is huge, and all of a sudden everything starts paging to disk, and wow, my app slows down when I get into a certain space on my video card, or my app runs for half an hour and then it slows down a lot and it's doing a lot of page swapping. This may be one reason, is because AGP memory is not swapped. Like I said earlier, this memory is basically uncacheable, speculative read-write combined memory. This is not coherent memory. What that means is that if you read to it, if you write to it and then you read from it, you're not guaranteed to get the same thing as if you we're using coherent memory. In coherent memory, reads and writes are guaranteed to be in order. So if you write data and you read data, you're guaranteed to get the right value. For write-combined memory, you're not guaranteed to get the right value. And this is set by the CPU MTRRs, as I mentioned. But the interesting thing is this whole DMA issue, direct memory access, where the video card can pull data, only works on coherent memory. It expects that if you write and then you read, you're going to get the correct value. And that is not true of non-coherent memory. So we need some way to access the non-coherent memory. And there's a couple of confusing ways to do that. Again, this is just to bring you up to speed on what these issues are. One is called pipeline mode. Basically, this is, think of this as half duplex, that the video card can issue some requests and then it has to get off the phone line and then get that data back. So it can have multiple outstanding requests going into main memory. The other way is called sideband. And think of this as full duplex. You can have simultaneous requests and simultaneous returns of data coming in at the same time. And for both of these, actually, here's one of the things. This is also in the bibliography that you can find these papers, agpforum.org. I always recommend it. I always try to read up a little on the technology I'm trying to leverage so I can get people to implement the features I want. So we talked about how you get to AGP memory. Well, now we're going to complicate the situation even more, because there's this thing called direct memory execute, or some people call it DIME. What it basically is, it's kind of like extended memory. You know, if you remember, the way expanded memory worked is that you actually had to copy data into your local memory or into a frame in memory in order to access that data. So if I were a video card and I did not have direct memory execute, I would have to go to main memory and say, give me a certain memory range that was, say, a texture. I would have to copy that data back to my video card, and then I'd have to access the bits from there. If I had something like direct memory execute, what I could do is I could basically treat that main memory that is AGP as extended memory space. So I could physically just go out, pick up the data, and use it immediately. So now that I've showered you with like a bazillion options, you can get a flavor of what the hardware guys have gone through to try and make the performance as high as possible. But a high-performing platform basically has a good chipset memory controller and a high-performing graphics card. Because somebody chose pipe or sideband or does DMX or does DMA or does one or the other, doesn't make them a bad part. What ultimately makes them a bad part is that they don't have performance. And we certainly know about some of those. So basically, the performance will be bounded by the lower performing component, no matter what it is. And so basically, this is a little chart that you can use to, if I'm in AG1X mode, I can do the memory mapped I/O just like in PCI. And whether that's coherent or non-coherent depends on my memory type range registers. I can do DMA, fast PCI, and frame if I'm in coherent memory. And I'm at least AGP1X. AG pipeline and sideband I can use in any of these modes. I can use DMX. They access non-coherent memory. And here's the part that just confuses everybody, is that a video card can combine these. They can use commands, they can send to memory map I/O places, they can DMA triangles from main memory, they can sideband access textures using DMX. And these are the choices that you have to make in order to make a good video card. So this means that different data will be banded by different rates. And I've heard a lot of people complain, wow, you know, I can transfer textures at such and such a rate, and I can transfer data at such and such a rate, and or actually I can blit at such a speed and I can texture at such a speed, but the speeds are different, but I'm basically moving texels. Why is that? This is why. Because they're implemented in probably different ways, or potentially different ways. So what we'll do now is, having all this newfound knowledge, we'll look at actually moving data between main memory, local video memory, and non-local video memory using something like Blit. We could have done this with things like texturing, primitives, and I'll talk about those in unanswered questions. Yes?
Do you know a way of forcing vertex buffers to be created in AGP memory?
Do I know a way of forcing vertex buffers to be created in AGP memory? Yes. Run DirectX 7.
Okay.
Whenever it's available. Okay. So basically the question we're asking is how fast can we get from A to B? Actually, just popping back to this Vertex, not to be too flippant on the point, but you get into all these issues. If the API is transforming, write combining memory is very slow because you can't read cache it. You get into just a ton of performance issues. So it's a very complicated question, and I don't think that was supported in DirectX 6. So basically, how fast can we get from one point to another? How fast can we get from main memory to non-local video memory, or non-local video memory to main memory? And one of the ways we have of actually testing this out is by doing a blit. But direct draw, for all intents and purposes, regardless of what actual functionality it may or may not expose in the hardware, is really just a heap manager. And you can allocate memory of any of these three types through direct draw. So what I did is I actually allocated 2 services of each type, and this basically gave me 9 test cases. And then I ran this on 3 different video cards in order to see what the performance was or how the performance varied in moving data between each of these 3 places. So from the pile of misfit cards, we selected the following 3 candidates. 3D Labs Permedia 2, and I know for those 3D Labs people in the audience, or the Intel people, or the NVIDIA people, here are the vendor, device, subsys, revision, etc., etc., etc. Because they'll think that's interesting. And this was all data gathered using get device identifier from the iDirectDraw 4 interface. These are the parameters that I iterated over, just like as I had done an experiment for the Vertex and homogeneous data versus heterogeneous data layout. This is the experiment that I ran for doing the Blit test, is that we had some surface width, and it started at 8, and I basically just bumped it up by 2 cache lines each time. Some surface height, bumped it up by the same value. Unanswered question certainly is these are square surfaces. What happens if I do a long thin one, or a long thin one vertically or horizontally? That's certainly a different type of test that could be implemented with the source code, but I'm giving out the source code so you can do it yourself. Plus there's a whole issue of queuing blitz. Basically there's hardware registers, or hopefully today everybody has hardware registers, in order to queue some number of blitz up. So I said, I don't think anybody could ever queue up 64 blitz, so let's queue up that number. And then I repeated each of these tests 10 times and put the results into Excel, selected the best time, and then graphed them. And I love graphs. This is kind of pseudocode, source code that's cleaned up. Please do error checking. All the error checking is taken into this code. I do error checking. I recommend error checking. Using the get timestamp counter, RDTSC, we took a start time, then we queued some number of blitz using blit fast. There's also an option to do regular blit. And then we took a timestamp. Basically, this is the guaranteed time. This is how fast I could stick it in the queue. So whether it's a 8x8 blit or a 800x800 blit, they should go into the queue just as quickly, but it should mean that I'm actually blitting more memory, technically. And then finally, we locked the surface and said, okay, we put all these blitz in the queue, how long did it actually take to complete? So now we know how fast we can submit them, and how we should know based on, well, let me back up and just preface this with today's CPUs and 2nd or 3rd or 4th generation graphics cards, whichever you want to call them, we deal with a lot of issues in parallel processing that some people may not be aware of, and we have a high degree of concurrency in order to analyze the performance of the graphics card. Thankfully, in terms of Blit, this is actually a pretty simple thing. When I was back at Intel and wrote the IP Graphics Performance Toolkit, I was using lock in order to also try and determine some other things, such as concurrency, performance, some other performance issues we can talk about afterwards. But basically, lock is no longer, with some of the current generation cards, and certainly with the next generation cards, going to be something that you can use in order to do that. You need more sophisticated analysis techniques in order to make a correct assumption on that data due to this whole parallel processing environment. So, pardon me if I step out. Like I said, I always have like 6 hours of data to cram into an hour. So basically, here is a single test case for guaranteed and completed throughput. And this was a 72 by 72 pixel surface. These are all 16-bit. And basically queuing 1 to 64 blits. So this is the guaranteed throughput on the yellow line. This is how fast I could stick the blitz into the queue. And on the bottom line here, this is the actual when I locked the surface and then did the divide. This is how long it took to complete. So we can see on this card, so we have blit 1, and since this was 72 by 72 by 2 bytes essentially, if I multiply all that out, I'll get some number. And that's close to a gigabyte a second. I'm being guaranteed a blit performance. In actuality, when I lock the surface, I find that it takes some good period of time. Now, the interesting thing to note here, and I'll get into this later when I actually name this perpetrator, is that we queue 1 blit, 2 blits, 3 blits, all the way to 32. When we queue the 33rd one, our performance drastically drops. Isn't that great? So, case 1, don't queue more than 32 blits. Yes?
Do you include the control case where you measure the cost of the lock and subtract the cost of the
Good question. Did I do a test case where I measured the overhead of the lock and unlock and subtracted it from the control case? The answer, in short, is no, because my assumption is with this data is that for very small surfaces, I know that I should be spending some of my time in the lock and unlock. Or actually, I'm just measuring the lock, so the lock's the thing that counts. I know I have a pretty good idea of what the lock overhead is from previous research, so I did not put that in here. One of the things that I could have done in order to make this data better, but I already thought it was good enough, given what I know about these graphic cards, because basically I already knew what some of these numbers were, so I was just creating a test to generate the data for today, so I could talk about them in a public place. But if I really wanted to get down fully to the metal, what I would have done is I would have taken this data and produced a linear equation and then subtracted back out the overhead of doing things like the lock and the API overhead. Does that make sense? But you're certainly welcome to modify the source code and the Excel spreadsheets and do that. And then post it back to the web and nail these bastards. So given that, what I then did is, having one test case, I then plotted the test cases one after the other on one graph. So basically you can see as the size of my surface, 8 pixels by 8 pixels, 72 by 72, 136 by 136 gets larger, basically I'm getting more guaranteed throughput. But as you can see on this card, what's happening is once I queue the 33rd blit, my performance drops to like essentially 0. And then, so this was guaranteed, and we can do the same thing with the completed megabytes a second as well. So again, 8 by 8, 72 by 72, and this is probably when 8 by 8, I could basically, without even going through everything to generate a linear equation, I could pretty much nearly take this performance, or even do a 2 by 2 blit, or a 1 by 1, and call that basically lock. Because it should take nothing in order to blit 1 pixel of the screen, and then subtract that out as pure overhead. So you can see what's happening here is I'm getting close to 200. I think the spikes above 200 are probably just outliers and don't really count. And then we can plot them both together. So you can see that actually guaranteed, I can guarantee something very quickly, because the guarantee is just sticking something in a queue no matter how big the surface actually is. But in terms of completion, it can actually take a while. And again, in the case of this card, don't queue more than 32 things or your performance just falls drastically. So let's start off by taking a look at main memory to main memory blit. This would be a standard main memory surface, write back. So it's read cached, write cached, snooped on the front side, et cetera, et cetera. Excuse me. And what we're seeing here is that we're actually getting our best performance probably for a somewhere between an 8 by 8 and a 72 by 72 surface. The reason I chose these values is that also running this data alone and running it 10 times was already taking an hour or more in some of these cards. And some of my coworkers, because I only have a certain number of machines of my own to run in, I was borrowing some of their machines, and they wanted their machines back. So there are also some things where the data will end, and that's just where I had to escape when they were like, okay, I'm back from lunch, you bastard, get off my machine. But what we can see here is that the main memory to main memory blit is about the same performance in each one. On some it's a little bit higher. That may indicate in some cases that some people in their drivers are actually taking over that instead of letting direct draw itself do it. And you'd have to get a larger sampling of cards in order to figure out if that was true. So can I make this main memory to main memory blit better? Well, it's already cacheable to cacheable memory. If you're already hand-coding your own blit, well, your own hand-coded blit will probably be faster. And if you're allocating a lot of main memory surfaces in direct draw to begin with, I'd have to question your implementation to some degree. I can certainly understand why you would do it, but it's probably better that you do all your own main memory surface handling. So, yeah. Oh, access your need. Oh, assess your need. It's spell checked correctly. So that was main memory to main memory. Let's take a look at local video memory. So this is the Permedia 2 performance that I recorded. Local video memory to local video memory blit. The completed throughput, as we saw when we had zoomed in earlier, way down here about 190 megabytes a second, even though we can queue a lot of things. The guaranteed throughput you're getting increases till you queue the 33rd blit, and then it drops precipitously. What that probably means is they probably have a problem in their driver or in their hardware or something. Maybe they have a counter in hardware that they need to say, is the blit queue free? Is the blit queue free? Is the blit queue free? You know, just wow one. And that's probably why they dropped there. I don't know for sure. If they told me, then I wouldn't be able to talk about it. This is what I brought up earlier, is that this is a zoom in that as far as when you get to the 33rd, this is the kind of performance degradation. So this means if I'm putting together something like my HUD, or I'm blitting on top of the screen, maybe I'm doing, I don't know, MPEG-2, I'm doing my own movie decoder, etc., that, well, I know that I don't want to blit that much, but that's just for this particular card. How do the rest of the cards hold up? Well, if we do take a look at something like the TNT, this is the original TNT, guaranteed throughput increases until the 8th blit and then essentially holds. I think that's awesome. Don't degrade my performance because I gave you more data. At least hold steady, and that's what this does. Completed throughput's also about 565 megabytes a second from this data. And again, it is probably higher if we went through everything to do a linear equation and subtract out the overhead. And it's very high concurrency. Everything just keeps getting better and better and better. This is an interesting graph. This is the Intel 740. Again, local video memory to local video memory. Guaranteed throughput seems to increase until the 8th or 16th blit, depending on surface size. That seems odd. It must be something weird, some hardware dependency or some driver dependency. And then it decreases. Completed throughput for this was approximately 150 megabytes a second. So basically, on this card, I recommend no more than about 8 blits queued at any one time. So this means if you're doing a lot of blitting, you either need to watch the number you do, reduce it, not do blitz at all, or break them up as you create your frames. So the bottom line is, even if you don't touch a local video memory surface, there's large performance differences. I mean, this was not us updating a video memory surface and then trying to use it as well. This was just going video memory to video memory. Never queue more than 8 blits. This is what this data tells me. I hope there's not a card out there that would ever queue less than 8 blits. There may be, I don't know. So potential performance optimizations would be interleave your blitz in other operations, do a few, do something else, do a few, do something else, which is always good in a parallel operation anyway. Aggregate smaller areas for blitting. If you're blitting 100 different things on the screen, try and make them larger areas because you know that you're getting higher guaranteed throughput. And replace blitted triangles with textured triangles. Yes?
I'm kind of confused. The two variables you had there were the guaranteed throughput and apparently the actual throughput?
Yes.
And the actual seemed to be rather constant, and the guaranteed would fluctuate wildly. Why is the guaranteed valuable piece of information? It seems like the actual throughput is the only valuable information.
Isn't the guaranteed throughput, aren't you just measuring how quickly you can queue things? It seems weird to be measuring queuing speed in terms of like megabytes per second.
Okay, let me answer both those questions. Why is guaranteed throughput the same? guaranteed throughput is the same because, well, I didn't go into it here, but once you do the any calculation, no matter how much data you write, can always be reduced to megabytes a second. And so once you reduce it to megabytes a second, it may take longer. It takes longer to write more data, but the megabytes per second is the same. Now the question is with the guaranteed throughput, why is it mapped in the same one? Well, yes, it's a little misleading, but it gets the point across not to queue more than a certain number of blitz.
But shouldn't that be mapped in terms of queues per second instead of megabytes per second? Then the graph for guaranteed would be flat also.
That it shouldn't be mapped in terms of queues per second. That is certainly another way that data could be displayed. It might be a better way.
So if you have more than 8 or 32 queues, you still get the same throughput, don't you? I'm confused. Why you say don't go more than 8?
What was okay? When we take the time. Basically, the queuing time increases when you have more than, say, 32 blitz on the Permedia. So you were actually spending more time in the blit fast call.
I see. Okay.
So maybe I was not clear on that point as well. Thank you. So getting from main memory to local video memory, this certainly impacts performance decisions such as, do I upload textures on the fly? For example, am I doing procedural texturing? Am I modifying things? Do I blit to the display during the game? The 740, well, as we can see in this case, the difference between doing a blit fast and then doing the lock took the same exact period of time. So what that tells me, first of all, is I have no concurrency, and I have to wait the entire time for all the data to be transferred. Same thing for the, let's see, this is the CPU pushing case. Pretty much same for the TNT and pretty much same for the Permedia 2 as well. I'm sure that if there was, you could do more analysis and figure out what would be a better way. For example, it might be better to do it as a texture. That's what we've seen in most cases, is that we try to avoid 2D operations at all costs and move things through AGP memory and texturing. One final chart, main memory to non-local video memory. This performance is a little bit better than we saw just going directly to local video memory. These, of course, are all AGP cards. And this is potentially better if you are doing procedural textures. Just put them into non-local video memory, but then the caveat is, can my card actually get blit information from non-local video memory to local video memory? And not every card can. So we end up all these special case situations depending on the card. So which way do I upload? Do I go to main memory to local video memory or to non-local video memory? Well, the performance is going to vary by the graphics card. Some cards, like I said, don't even support non-local vidmem to local vidmem blitz, and unfortunately your mileage may vary. So let's talk about some unanswered questions. Again, this is what I mentioned before, the blit of non-uniform areas, very thin, vertical areas, very thin horizontal areas. Those will probably have different performance characteristics than just doing a square area of blit. The performance of texture transfers itself, the blit may in some cases approximate or even equal performance for transferring textures to the graphic controller that don't rearrange the texture contents for higher locality. What a lot of graphics cards will do is they will actually rearrange the bits of your texture in order to get better cache consistency on their own. But a specific test would be required in order to test this, and then you have to take into account things like texture size, direct sampling, upsampling, downsampling, nip maps, etc. A number of things to be tested here. And there's also, again, the question of primitive data transfers and command transfers to video cards. The type of primitive, the number, is it, for example, talking about the triangle primitive, discrete triangles, strip triangles, fan triangles, what options do I have in the card? How does the option that's in the card slow the card down itself so that it either pulls stuff out of the pipeline more slowly or otherwise adversely impacts performance? So just some of the unanswered questions, although I could unanswer a whole lot more. Let's see, collateral and bibliography. Let's see. This presentation, the paper, the foils, the two demo programs, one to do the Vertex test and the one to do the Blit test, and 40 megabytes of spreadsheets. Woohoo! They're on gdconf.com. I don't know where. I'm a speaker. They don't tell me these things. It's also at our Ensemble Studios website. It'll be there probably about Wednesday or so, once we actually get back under the developer news section. Check the AGP Implementers Forum, agpforum.com. There's CPU and AGP information at developerintel.com, and certainly vTune 3.x, or I guess 4 will be coming out soon as well. Some books, David Lotion, Efficient Memory Programming. That's a new book. It's an okay book. It's certainly a good introduction to efficient memory programming and the way you need to restructure your loops, code, etc. A couple of books from Mindshare by Tom Shanley and Don Anderson. Pentium Pro Processor System Architecture and PCI System Architecture. The P Pro book is the latest of theirs. They don't have a Pentium 2 one yet, but that will tell you all about MTRRs, settings, cache, registers, etc., etc. And when all else fails, AltaVista, or there's also Copernic, which will search multiple sites.
That concludes this program. You may order other audio recordings of this conference or gather information about recording services by contacting The Sound of Knowledge at area code 619-483-4300. Email us at sales@tsok.net or visit our website at www.tsok.net.